All right, so 5.3 is a crucial section in all of calculus. Really, it's going to be the most important section that we cover in chapter 5, and it's in this section that we're going to cover the fundamental theorem of calculus, which is, as the name would seem to imply, the most important theorem in the entirety of calculus. What it's going to do for us is give us a very useful technique for solving definite integrals, for evaluating definite integrals without the need for that limit definition of the integral that we talked about in the previous section, without the need for approximations or geometric formulas, which, although useful, are rarely usable. The function has to have a graph that resembles some common geometric figure for that to work. So what we're going to do here is start by working up towards the first part of the fundamental theorem of calculus. There's two parts to it, and the second part is the one that we're going to be using the most, but the first part helps us get to the second part. In order to cover the first part of the fundamental theorem of calculus, we have to introduce something that we call an integral defined function. So if we suppose that f of x is this should say integrable, little typo there, integrable function, then we can define g of x equals the integral from a to x of f of t dt, where a is some constant. What we're doing here is we're using an integral to define a new function from an old one. The a here, it can be any constant, but the key thing here is that the x that's showing up as the input for g is the upper limit of integration in this integral. Now normally, you notice I defined f of x here, but then in my integrand I called it f of t, then there's my dt. And the reason for that, we introduced the t here, which is called a dummy variable. Its purpose is to not duplicate the x that's showing up in the upper limit of integration here, because then that would apply some connection between this x and that x, and we don't actually want that. So even though it was defined with an x here at first, we did say when we define the integral that you can swap this variable out for any other variable as long as you do the same with your dt in this case instead of a dx, and the end result still comes out the exact same. So it's okay to do this when necessary, and this is one case where it's necessary. Okay, how do you interpret this function though? What does this actually do? So let's use an example to sort of illustrate how this kind of function works. Let's suppose that f of x is the function that's shown here in this graph, and we're going to define g of x to be this type of a function where our constant a is chosen to be 0. So it's the integral from 0 to x of f of t dt. And we're asked to evaluate several values. What is g of 0? What is g of 1 and g of 2, and so on and so forth? Well, this came straight out of your book, and so I'm using the results in your book. And we have all of the answers down here already except for g of 0. Let's talk about g of 0 first. What would g of 0 mean? Well, I'm looking for where that input goes into my function, and it goes into the upper limit of integration here. This would equal the integral from 0 to 0 of f of t dt. And I don't even need to look at the graph to know what that looks like, because we saw in when we talked about properties of the definite integral that if you have the exact same upper and lower limit of integration, this always comes out to 0, no matter what's going on with that function there. So that's an easy one. But for the others, g of 1, what does that mean? Well, g of 1 means this, the integral from 0 to 1. The 1 becomes my upper limit of integration of f of t dt. Now, how do I evaluate that integral? Well, now that I have a graph to look at, I'm looking at the area under this curve from 0 to 1, which is shown here. It's just highlighting that specific part of the graph. In this case, I do get to use a geometric area formula because we have a right triangle here. The base is 1, the height is 2, so 1/2 base times height, 1/2 times 1 times 2 would equal 1. Okay, and that's why we're seeing g of 1 equals 1 right here. G of 2, what is that? Well, g of 2 would equal the integral from 0 to 2 of f of t dt, which would equal, or which would correspond to the area under the curve from 0 to 2, shown here. We've already found the area of this triangular portion. We said that that was 1. And the rectangular portion, you notice there's a rectangular portion right here, has a width of 1 and a height of 2. So that would be 1 times 2, or 2. 1 plus 2 gives me a total area of 3. G of 2 equals 3. And so you notice plugging in different values for the x in this function is giving me different areas to look at, always starting at 0 and going out to whatever I'm plugging into my g. Okay, so the next part of this, g of 3, you'll notice the next portion of our graph looks kind of like a piece of a parabola or something like that. And in this case, we're kind of estimating that area because we don't have, we haven't developed a good technique for finding that area explicitly yet. You notice if I were to join this point to this point with a straight line segment, if I did something like this, I'd have a right triangle with the exact same area as this right triangle. That would have an area of 1, but we can see that there's more area out here. So the additional area being added to this has to be a little bit more than 1. Your book gives about 1.3 for that area. You see approximately 4.3, which is the previous area, 3 plus 1.3. And then you have another parabolic region down here. So when we plug in a 4, g of 4, you can see that we get a parabolic, like part of a parabolic region right here, which seems to have the same area as this region up here. Just by kind of eyeballing it, they appear to have the same sort of shape to them. And so we would expect this area, which will come out negative because it's below the x-axis, to potentially just cancel out the area that we added in the previous step, leaving us with 3 again. And then if we, plug a 5 in, g of 5, we're going all the way out here. That accumulates more negative area. And we said that the area of, half of this little parabolic region back here is approximately 1.3. So we'd probably subtract 1.3 from 3 to see what the net area is here, about 1.7. Okay? So that's kind of the idea behind these integral defined functions. Again, what you're plugging in for x is determining the upper limit of integration, which is telling me how far out to go to determine that area under my curve. Okay, so integral defined functions. Now, with this concept of an integral defined function, we're able to find a really, really fascinating connection between the definite integral and the derivative. Now, at first glance, it might seem like these two concepts don't have anything to do with each other. The derivative, we came up with that concept when we were looking for slopes of tangent lines to functions, or to the graph of a function. So derivatives seem to have to do with slopes. Integrals, the definite integral, we defined when we were looking for areas under a curve. And so area is the underlying concept behind a definite integral. Why those two things don't seem to have anything to do with each other. But the fundamental theorem of calculus is going to show that the two are intimately related. So here's where we're starting to build on that concept. Now, we're going to prove this when we get to the fundamental theorem of calculus, but it turns out that if you have an integral defined function like what we've defined, g of x, if f of x is a continuous function, then the function g of x will end up being differentiable. And that's kind of the first step in proceeding with what we're going to do here. Now, if we know that it's differentiable, it's reasonable to want to try and find what its derivative would look like. So how do you find derivatives? We start with a difference quotient. Let's suppose that our function g of x is differentiable on, let's suppose that f of x is differentiable on this, actually, we really just need it to be continuous, but continuous, I should say, on the closed interval a, b. And let's select some number x somewhere between a and b. So I can say that that puts it in the open interval a, b. It actually doesn't need to be in the open interval, but it kind of works better with this picture to assume that it is. And then we're going to choose a value of h that's small enough, meaning close enough to 0, so that x plus h is still inside that interval. So this graph here is kind of showing what I mean by that. If I choose x here, I'd like to choose a small value of x so that x plus h doesn't take me outside of that interval. I want the x plus h to stay on the inside so I can do something with it. Okay. In the attempt of building a difference quotient, we know that in a difference quotient, the numerator looks like, if our function is g of x plus h minus g of x. Okay, and then we're going to end up dividing by an h eventually, but let's just look at this part first. What does this look like in thinking in terms of how the function g of x was defined in the first place? Well, g of x plus h is the integral from a to x plus h of f of t dt. Remember, that input just ends up as the upper limit of integration in this integral right here. G of x is exactly this, the integral from a to x of f of t dt, so it shows up here. Now, we talked about a property of the definite integral that says that if you reverse the order of your limits of integration, then you get the opposite of the integral that you had in the first place. So I'm going to flip these limits of integration in the second integral here, so it goes from x to a instead of a to x, which would effectively change that minus into a plus. Now I'm going to use another property of integrals, which says that if you're adding two definite integrals with the same integrand, f of t dt, and if the lower limit of integration of one of my integrals matches the upper limit of integration here, so a and a, you can combine these into a single integral where you have the lower limit of integration from this guy and the upper limit of integration from that guy, x to x plus h. Okay, so we use two properties of the definite integral. Notice I don't need to know anything about the function f of t here. I can just use these properties. Okay, now think about what this integral technically represents. This would be the area under the curve, under the graph of y equals f of t, which is this graph that we're using right here as an example, on the interval from x to x plus h. So we're looking at the area of this blue region right here. Okay. Now again, remember we chose h to be very, very small. So that blue region is probably going to be pretty well approximated by this rectangular region. But what can I say about this rectangular region? Well, I'm using a left endpoint here where x determines the height of that rectangle. So the height would be f of x, and the width of that rectangle was specifically chosen to be h. So that means that the area of that rectangle is h times f of x, width times height. Okay, and like we said, we chose h to be small, and so the area of that rectangle is approximating the area of this blue region, which was found to be the same thing as g of x plus h minus g of x. Okay, so g of x plus h minus g of x is approximately h times f of x. Dividing both sides of this by h and keeping that approximation sign here shows me that the difference quotient, g of x plus h minus g of x over h, is approximately f of x. And it would seem that if you look at the picture up here, if h is taken to be smaller and smaller and smaller, the amount by which that rectangle is missing the actual area of this region here, that we'll call that error. So this rectangle has this little gap here, which I'm going to call error in my approximation. That error is getting smaller and smaller as h gets smaller and smaller. I'm expecting that error to shrink to 0, which means that this approximation would be made exact as soon as I take the limit as h goes to 0. So that seems to suggest that this limit, which is the same thing as g prime of x, is equal to f of x. In other words, if I take this integral function and differentiate it with respect to x, the derivative and the integral in a certain sense cancel each other out and leave me with just the integrand, f of x. The t gets replaced with an x at that point. We didn't prove that, we just kind of provided an intuitive argument for it, and so we're going to prove that on the next page. And this is what we call the first part of the fundamental theorem of calculus, or we're gonna call it FTC 1 for short, fundamental theorem of calculus part 1. So here's what the first part of the fundamental theorem says. If f is continuous on the closed interval ab, then the function g, defined the way that we've defined it before, where x is any number within that closed interval, will also be a continuous function on the closed interval ab. It will also be differentiable on the open interval ab. Does that sound familiar? And g prime of x will equal f of x, which is what our argument on the previous page was trying to show. Okay, so how do we actually prove this? The proof is a little bit involved, but we have all the tools that we need to understand it. It actually relies on some theorems that we've discussed before. We're going to use the extreme value theorem in this one. So first of all, it says if x and x plus h are in the open interval ab, then g of x plus h minus g of x is equal to the integral from x to x plus h of f of t dt. This is the same argument, essentially, that we made on the previous page. They just kind of, they do make it look a little fancier than I did, but it's essentially the same argument. So if h is not equal to 0, then g of x plus h minus g of x all over h is equal to 1 over h times, again, this integral. Basically just multiplied both sides of this by 1 over h. Okay? So for the first part of this proof, we're going to assume that h is positive. That's the assumption being made here. And since f is assumed, we assume that f is continuous on the closed interval ab up here. The interval from x to x plus h is going to be contained in the interval from a to b. So if f is continuous on the closed interval ab, as stated up there, then it would also have to be continuous on this closed interval from x to x plus h. So knowing that, if we know that if a function is continuous on a closed interval, that's what allows us to apply the extreme value theorem. We'd apply the extreme value theorem on this small interval here. And the extreme value theorem says that there has to be some numbers, they're calling them u and v in this proof, such that f of u equals little m and f of v equals capital M, where little m and big M are the absolute minimum and maximum values of f on that closed interval. Remember, the extreme value theorem says that if you have a continuous function on a closed interval, then that function will attain an absolute max and an absolute min on that interval. That's what this is saying. Little m is the min, big M is the max. So what we're going to do now is use one of those many properties of integrals that we talked about previously. Looking at my integral here, first of all, getting rid of the h's here for a second. This, so the property 8, I think I have that one on my notes here for reference. It'll be easier if I can show it to you. Here we go. This is from section 5.2. Here's property 8 that it's referencing. If a function has an absolute minimum of little m and an absolute maximum of big M on some closed interval, then the integral from a to b of f of x dx is between these two values, little m times b minus a and big M times b minus a. B minus a is the length of the interval that you're integrating over. Okay? In this case, instead of an a and a b, our limits of integration look like an x and an x plus h. And the difference between these two numbers is just h. So that b minus a that we saw in property 8 becomes an h here and here. Okay? And so what this means is that little m, which is equal to f of u times h, and big M, which is equal to f of v, if we multiply that by h over here, are the lower and upper bounds of this integral. Okay, that means that this interval takes on a value somewhere between those. Now, since h is positive, remember we assumed that is positive, we can then divide all three of these parts by h to get this. F of u is less than or equal to 1 over h times that integral, which is less than or equal to f of v. Okay, and then we are going to replace the middle part with this expression here, this difference quotient, because we know that this is equal to this. Okay. Now, we could go through a similar proof, which it's stating here, if we also assume that h is negative, we just get kind of a flip-flop of those inequality signs, but nothing important is affected by that. So with that in mind, what happens if we let h go to 0? Because that's going to turn this difference quotient into a derivative if we take the limit as h goes to 0. What's happening to the outsides here? Well, excuse me. Think about where u and v live. They live inside this closed interval from x to x plus h. And if h is shrinking to 0, then x plus h is going to approach x. This interval is shrinking down to a single number x when that happens. Okay, but that means the u and the v contained in that interval that are showing up here and here are also shrinking up towards x. They're approaching x. Okay, so the limit as h approaches 0 of f of u is equal to the limit as u approaches x, using that argument of f of u, which would just be f of x. In a similar case over here, f of v will also approach f of x. And so now what we have is a compound inequality where the lower bound is approaching f of x and the upper bound is approaching f of x as h goes to 0. This looks a lot like the squeeze theorem. And in fact, we can apply the squeeze theorem here, and it would say that if these two things both go to f of x as h goes to 0, then this also has to go to f of x as h goes to 0. So applying the squeeze theorem, here it is, yeah. G prime of x, which is the limit as h goes to 0 of that difference quotient, is equal to f of x. Okay? So that basically completes that proof. And they make a little statement here that kind of justifies why we can say G is continuous as well. But again, trying to reiterate what I had said before, this theorem here, G of x is equal to this integral defined function. And if that's the case, then G prime of x is equal to f of x. In other words, if I differentiate this thing, I get the function on the inside, with the t replaced by an x. And I can write that in Leibniz notation this way. D dx of the integral from a to x of f of t dt is equal to f of x. What this effectively means is that the integral and the derivative are inverses of each other. Inverse operations are something you've talked about since pre-algebra. You know, addition and subtraction are inverse operations. If I add 2 to a number and then I subtract 2 from that result, I get back to where I started from. One will undo the other. Multiplication and division are also inverses of each other. Differentiation and integration are inverses of each other in this sense. Okay? So let's use this theorem with a couple of examples here. This first one, g of x equals the integral from a to x of the natural log of t squared plus 1 dt. We want to find g prime of x. Well, the fundamental theorem of calculus, part 1, says that g prime of x is just equal to the integrand itself, natural log, with my t's replaced by x's, x squared plus 1. That's it. There's nothing more to do there. The fundamental theorem of calculus tells me that has to be the case. Now there was a condition here where it said that the function had to be f, the integrand, has to be continuous on the closed interval ab. This function, the natural log of t squared plus 1, is actually continuous everywhere. So definitely on the interval from a to whatever b happens to be. Okay, so that's it. There's nothing to do, nothing more to do. This one's a little bit more involved, and the reason for that, even though I'm taking the derivative of an integral defined function, look at the limits of integration on this function. The issue with that is it doesn't take the form that g of x takes here. What we need in order for this to work, we need a to be some constant. So my lower limit of integration needs to be some constant, and my upper limit of integration needs to be just an x. Okay? So what I'm going to do is I'm going to define g of x to be the integral from 0 to x. Now I'm choosing a 0, and it doesn't have to be 0. I know somebody's going to ask, why did you choose 0 here? It can be any constant at all, as long as the function is defined there. The tangent function is defined at 0, so that's not going to cause any problems for us. Okay. Now there is kind of an underlying assumption here, which I'm not going to make a big deal about, but the tangent function does have discontinuities because it has asymptotes. So we're kind of assuming implicitly that x is in the first quadrant of the unit circle, because this has to create an interval on which the tangent function is continuous. But I'm not going to state that explicitly. That's just kind of an assumption going on in the background. Okay. Tangent of x dx. Okay. Oh, I was supposed to put t's there. Forgot my dummy variable. G of x is equal to the integral from 0 to x tangent of t dt. Okay. So what I need to do is kind of rewrite this integral that I'm trying to differentiate here using some integral properties. So what are we going to do? We're going to write d dx of the integral from x to x cubed tangent of t dt is equal to this. It's equal to d dx of the integral from 0 to x cubed tangent of t dt plus the integral from 0 to x tangent of t dt. Now, what property did I just use? Well, it's that property from back in section 5.2 that says as long as the integrand is the same, I can split an integral up into 2 as long as the lower limit of integration matches the upper limit of integration in the other integral. Okay, so this is starting to look right. But there's an issue with each one of these integrals. The second one is the easier one to deal with. Let's leave the first one alone for a second. This is equal to the integral from 0 to x cubed tangent of t dt. This one, the limits of integration are in the wrong order. The first part of the fundamental theorem of calculus said the constant needed to be down here and the x needed to be up here. But I can fix that. I can switch the order of integration and just put a minus out here instead of a plus. We've already used that property. So that's not too bad. Okay? Now, d dx. This right here is g of x, right? But what is this? It almost looks like g of x, but where I had an x here, it becomes an x cubed. So it's kind of like plugging an x cubed in for x here, which means this integral could be written as g of x cubed. That makes it a composite function. Minus, this guy looks exactly like g of x, so I can just do that. Okay? Now, what am I going to do next? Well, I need to take the derivative of this thing, and I'm going to distribute my differential operator into each one of these. We know that's a property that exists. So that would take the derivative of this and the derivative of this. But what is the derivative of that first term? Well, because it's a composite function, I need to use the chain rule. That's g prime of x cubed times 3x squared times the derivative of that inside function minus g prime of x. Now finally, the fundamental theorem of calculus, the thing we just talked about, tells us how to find g prime of x. G prime of x is equal to tangent of x. It's the integrand where the t has been replaced by an x. So that means I'm looking at tangent of x cubed now times 3x squared. I'm going to bring the 3x squared out front. Minus, this would just be tangent of x. And that's my answer. Obviously, that was much more involved, but I needed to use some properties of the integral, the definite integral, in order to get there. The key thing to remember is that in order to apply the first part of the fundamental theorem of calculus, your integral has to have this form to it. It has to have a constant here and an x up there. Okay? This video has gone on long enough. Let's go ahead and stop this one here.